Hello there, I'm Thomas. This is a British American pilot flying the Boeing 777-300ER international flight from Zurich International Airport. We're going to be over flying Zurich, Switzerland, Germany. Then coming back to Zurich International Airport, runway 14 for now. Let's localize our landing sternum, the cockpit for the pre-takeoff preparation of the Boeing 777-300ERX of the PMG simulation and Microsoft Flight Simulator X. I'm going to start showing you the cockpit instruments and the display and the function of the Boeing 777-300ER airplane. I'm going to start with the primary flight display that displays the airspeed indicated, the ground speed, the airspeed selected from the autopilot and direction system panel, the radio altitude above the ground level, the barometric pressure of the outside atmosphere, the barometric altitude selected from the autopilot and flight direction system panel, what is the target altitude, and also the barometric altitude of our own aircraft above the sea level. We also have the magnetic North Pole and the true North Pole and the magnetic variation depending on where we are in the world. We have the altitude indicator with the pitch ladder in degrees and the bank angle in degrees, also the Lszh localizer crossbars and the flight director crossbars for manual guidance of the aircraft, and we have also the autopilot crossbars for automatic guidance of the aircraft. We have the angle of attack of the aircraft as it flies, and also the flight mode annunciator with the autopilot and the autothrottle, later on vertical navigation modes. We also have the navigation display. The navigation display that displays the airports, the waypoints, the navigation aids, the GPS position of the aircraft, and inertial reference position. the magnetic North Pole and True North Pole, and the magnetic variation depending on where we are in the world. We have also the terrain and weather reflections from the weather radar of the aircraft. So we can see the terrain depicted with an elevation of green, yellow and red colors, and also we can see the sea, the lakes and the rivers with blue. So we can see also other aircraft flying around aircraft using the transponder, the ADSP and ADC transmitter receiver that transmits and receives around frequency, and also this generates TICAS system trans-collision alert system warnings, so you can see other aircraft incoming collision alerts and other warnings. So you can see other aircraft, how far away they are from our aircraft, their distance in nautical miles, their heading, their airspeed, and also the altitude difference from our own aircraft. So it does, this also transmits our own data to other aircraft and to the air traffic control. And we also have the autopilot and flight director system panel, the FTS, so you can see the autopilot engage and disengage switch, the auto throttle left and auto throttle right engage and disengage switch, the flight director engage and disengage switch, the flight level change, you can use the airspeed select node, so you can see you can set the airspeed of your desire as you fly, as is necessary. So this will generate an airspeed command using the auto throttling, the auto thrust system of the Boeing 777-300ER. So we have some ones like you can select an airspeed in nautical miles per hour, not so Mach speed. So you can select the flight level change, the AT, the auto throttle hold switch, with the speed mode and also the climb mode. So we have two main kind of modes for the autopilot and the auto throttle. We have the climb continuous. We have the fixed thrust mode, it's like the climb continuous or the takeoff go on, and also the idle thrust for descent, which generates some fixed thrust mode settings for the engines. We have the General Electric 90G90 turbofan turbojet engines installed in our aircraft, and this will generate a fixed thrust like in the climb or the descent or the takeoff go around. So we have the airspeed is being adjusted as we climb or as we descend by increasing or decreasing the rate of climb or descent using the horizontal string stabilizer command orders or the elevator of the aircraft to control the rate of climb or descent, as we have a fixed thrust. And also we have the variable thrust mode like in the cruise or the approach and landing, so you can use this mode also for in which the thrust of the aircraft is being varied to actuate the airspeed, while we have the altitude of the aircraft like in the cruise level hold constant. So we have also the bank angle select node. We have the heading hold, the heading select switch. We have the heading select knob and the heading hold switch. We have the vertical rate of climb descent of the aircraft in tens, hundreds and thousands of feet per minute, or its trigonometric angle in decrease, which is the FPA, the flight path angle, or the VS mode. You can see the vertical speed indicator in the primary flight display with the rate of climb and descent of the aircraft. And also we have the altitude select knob and the altitude hold switch, the VOR localizer, switching the approach switch for the auto run function of the Boeing 777-300ER. So we have other stuff also, other instruments and functions. So we have the thrust control of the aircraft. You can see here the thrust levers. You can see the yoke here, which controls the flight controls. You can control the elevator up and down, and the ailerons and the spoilers left and right, and also the rudder, the vertical stabilizer rudder using left and right. You can use also the horizontal trim stabilizer or the rudder trim and the other instruments I'll talk to you about later. So the thrust levers, we use the thrust levers to control the thrust produced from the turbo-contributed engine. We have the General Electric 90G90 turbo-contributed engines installed in the Boeing 737-300ER, one on the left wing, one on the right wing. We have also the FAREX, the Cool Authority, which is electronic control computers that control and monitor all the display that you see, all the information about the engines in the upper and lower ACAS and indication controller system display. So I will talk to you then about the flight schedule of the aircraft, how we can calculate the takeoff speeds using the data we input in the flight management computer, like the takeoff weight, the fuel on board, the reserve fuel, the taxi fuel, the passenger and the cargo on board. This generates using the flight management computer a minor dynamic chord position with the center of gravity of the aircraft as trimmed by the horizontal trim stabilizer of the horizontal tail, which balances the aircraft as it flies, and also you can make it climb or descend. So we're gonna use this data. We're gonna use the flight management computer also to create a route complete takeoff using the departure airport runway. We're gonna select the seats, the starter instrument departures, the intermediate waypoints, the destination airport and runway with an Lszh localizer approach, and also the stars in starter terminal arrivals. Fixes for the vertical and horizontal profile of the aircraft. We're gonna have a complete route or complete flight plan or a flight path for the aircraft to follow using manually by flying it manually or using the autopilot and the autoflow input. So we're gonna generate this route using the flight management computer. It's gonna be depicted on the navigation display, so you're gonna see a purple line with the departure runway and the destination runway. We're gonna have also the runway data, like the length of the runway, the elevation above the sea level, the temperature of the air, the density of the air, the barometric pressure, and the wind speed direction, and other data like the runway conditions, if it is dry, wet, or ice, and as I told you, the speed of the wind, which also affects the takeoff. So we're gonna use the flaps and the horizontal trim stabilizer for this flight. Then I'm gonna show you the overhead panel. I'm gonna show you the electrical left and the right engine driver. IDZs, the great drive generators that produce alternate current 120 to 200 volts, 400 Hz frequency, three-phase current. You're gonna see we have the left and right IDZ, the great drive generators, which is driven by the engine gearbox using horizontal drive shaft. So we're gonna have this alternate current 120,000 kilovolts or 100,000 watts. We have also the backup generators, another 25,000 watts each, and this is for the left and the right engine. So we have two IDZs. We have also the batteries, 38 volts, 40 average direct current. We have also the APU, the auxiliary power unit, which has another 130,000 kilovolts or 100,000 watts of alternate current, 120 to 200 volts, 400 Hz frequency we need for starting the engine. So as a backup in flight, we use the APU, the auxiliary power unit, which is a smaller turbine in the tail of the aircraft. Also, this is supplied with fuel from the left wing tank, as you're gonna see later. We have the left wing, the right wing, and the standard tank in the aircraft, which supplies the engines and the APU with fuel. And we have the forward and the aft fuel booster pumps, and the crossfeed valves and the fuel flow, the low and high pressure fuel control fuel levers in the left and right engine. I'm gonna show you also the hydraulic system, the left and right engine driving hydraulic pumps and tanks, and also the C1 and C2, the electrical interface drives from the engine. We have also the rammer turbine, the passenger auxiliary, the fire extinguishers for the cargo and the engine. We have also the electronic engine control for the engine left and right engine auto start system, which also controls the ECU's electronic engine controls the paddock, which will control the electronic control computers. We have the ability air data reference unit. We have the primary flight control computers. We have the wing and engine guides. We have the cabin pressurization system on the aircraft. I'm gonna show you also that. After the seats pressurized from the left and right engine of the view, have also the left and the right engine pressurizer system, the bleeder from the fifth and the ninth stage of the engine. You're gonna see also that. So we're gonna have also the bleeder that supplies the wing and engine guides, the air conditioning and ventilation, and also the hydraulic fluid system and the cabin pressurization of the aircraft. Then I'm gonna show you also the radio management panel with the radios and the navigation aids. So thank you very much one more time for watching. I'm Thomas Hatsios, the British American pilot flying the Boeing 737. We are in tonight's flight. I'm gonna start now showing you the cockpit of the aircraft. So you can see here we have about an hour left for this video to end. So yes, this is an hour. So you can see inside the aircraft. You can see again I'm using the controls. This is the outside view. Hope you like it. So I'm gonna start now the explanations of the systems. You can see the overhead. You can see also the outside view. So I'm gonna start now with the primary flight display. You can see here we have the airspeed tape with the airspeed indicated to the airspeed selected from the autopilot and flight director system panel. With purple, the ground speed is 0, the radiality of the ground level, the magnetic heading and track. We have the barometric pressure of the outside atmosphere. We have the altitude of the aircraft above the sea level, that is our own airport elevation. We have the targeted altitude selected from the autopilot and flight director system panel, and the vertical rate of climb or descent of the aircraft. You can see the needle is moving up and down when we climb or we descend. We have the primary flight display with the pitch ladder in degrees and the bank angle in degrees. So you can see 2.5 degrees are tick marks. 5, 7.5, 10, 12.5, 15, 17.5, 20 plus or minus. Climb or descent. We have also the takeoff go around the flight mode and unscheduled with the autopilot later on with the navigation mode. We have the navigation display. You can see in the navigation display we have the terrain map and the airports. You can see here is Switzerland, here is France, and here is Germany over here. So you can see our position. This is our airport, and we're gonna see later the route. You can see 6,100 feet is the maximum elevation depicted with red, and 0 feet with green is the minimum for this display. You have magnetic heading and track. You can say it's magnetic or true. Now we have the geographic North Pole over here depicted. It's a little bit different for this area. Now we have again the magnetic, the normal. So we're gonna have also inches of mercury meters. You can see we have the target only in meters. We have also hectopascals over here for the barometric pressure, depending on where we fly. We have also the autopilot flight director system panel, auto throttle left off, auto throttle left on. So you see the auto throttle, the warning over here is off. We have on the right auto throttle on. So we have auto throttle right off and auto throttle left off. You're gonna see the opposite. So we have auto throttle right off. We have also the flight director on and off. flight level change here, flight director you see on and off. Over here this switch. We can use select a different airspeed for takeoff than the one pre-selected. We have indicator airspeed or Mach, we have the LNAV and the VNAV, the flight level change again. So we're gonna use this airspeed. We have the autopilot on like this, pressing this switch is the green here. Now we have the autopilot connected. We can disengage the autopilot like this by pressing out this switch here. So you're gonna see the warning here coming up. The warning, and the autopilot is disconnected with red color over here in the upper ACAS. So we press in again this and we continue with warning off. So we have again this mode, the bank angle, select, we leave it in the auto. You can select or deselect it by pressing this switch. So we will select a heading of 136, the vertical speed, flight path angle. So you will select a descent, the altitude select, change vertical speed. So we have the negative here, flight path angle. You will see the negative to distinguish a descent, or the positive to distinguish a climb. You will see here in the primary flight display the indication with the tick mark. Here now is the descent, the 3.5 degrees descent path. So we have this target altitude, flight path angle and heading select, 35,300 feet or 7,710 meters and 253 meters nautical miles per hour. And we have the hectopascals. We can set radius of mercury again over here. So now we're gonna set the positive, the climb. So it's plus 3.5 degrees. You would see plus 3.5 degrees between the 5 and between the 2.5 and the 5. So you see it's here the tick mark. So now we use also the vertical speed in feet per minute. So you will see the descent here like 3,000 feet per minute. You will see the descent path. We have to follow over here in the tick mark in the rate of climb over here, the purple, and we have the climb over here. You will see the climb like 3,500. So you see 2, 3. We have again the meters display, the vertical speed. You can see the difference between the two modes, and we have 36 minutes gone. So we have, now we're gonna select maybe the autopilot on. You will see this mode with the autopilot connected. Now we can use the flight level change again with the autopilot. So we have the flight level change speed here. We can select the flight level change with heading hold together, heading hold and flight level change speed. and we can select either flight level change or altitude or vertical speed. So now we have the altitude connected. So this is all the modes, as many as you can see. You can see other aircraft flying closer or farther away from you. You can see one is coming here in the radar display. It's 2,400 feet above us. You can see its indication now is 2,300. It's descending and it's coming closer and closer to us, to the runway for landing. Now it's 2,200. You can see it's in front of us. You will see it in a couple of minutes. Now it's 5 nautical miles in this ring, and it's getting closer and closer. Now it's plus 1,700. It's getting closer, and this line in front of us is coming for landing. You can see it is coming, coming aircraft for landing. Plus 1,300. It's coming down. It's descending, and you can see it's blinking. It's getting closer and closer. So this is how you can spot an aircraft in the navigation display using the transponder transmitter receiver, which acts as a passive radar. So you can see using the traffic other aircraft coming. So now it's about less than 2.5 nautical miles away. It's 2 nautical miles away from us, and it's only 600 feet above the ground level. 500 feet. It's getting closer. .500 feet is getting closer, and it's coming for the landing over here. As you can see, 500 feet above the ground level. Now it's about you can see the warning over here is getting yellow. Now it's 200 feet above us, and it's in front of us. So now we can see coming for a landing. And here we are. We have our aircraft just landed. A Boeing 737. So we continue now with the other systems. We'll see how to use this system, also very important. So now I'm gonna show you also how to disconnect the autopilot. As I show you, see the autopilot is disconnected like this. We re-engage by pressing this switch. So you see the green here, and the autopilot is on here. We can also press or move the wheel, so you can press this, the autopilot disconnect. You will see again the autopilot is disconnect, the warning. And we have the warning here, and the autopilot is disconnected. So we press one more time to confirm the disconnection and cancel the warning. So this is the autopilot disconnect and we have about 30 minutes left. So now you can use the manual inputs. Now we'll proceed to the next section, the upper and the lower ACAS. So you can see here we have the information from the engine. You can move the engines forward or aft, the thrust levers. We have you can extend the speed brake over here. You have the thrust levers at idle only. If you move them above the idle, the speed brakes retracts automatically. This is the parking brake. Also you can see Here we have the flaps, which increase the surface area of the wings, so you can retract or extend them as many degrees as you wish. You have the speed brakes, as I said, extend and retract, the parking brake, up and down. This is the horizontal trim stabilizer of the aircraft. You can see the horizontal trim stabilizer. You can pitch trim or pitch down the aircraft nose like this. We have the aileron trim. So you can see the pitch trim and the rudder trim, and the aileron trim is here, the rudder and the ailerons. You can see the rudder position here. We have the pitch trim of the horizontal tail over here, so you can see nose up and nose down. You can see how many degrees you have it, and you can set in the green bud for takeoff, or as you use the flight management computer over here. I'll show you later. We have also the fuel control for the aircraft, the left and the right engine. We have the fire extinguishers for the left and the right engine. We have the radio and communication panel of the aircraft. Over here you can tune the radios, and also use the weather and terrain radar, and also the transponder, the DSP and DSC. You can see the TCAS system. Select the traffic warnings. You will see generated traffic from the TCAS system if you have other aircraft flying around you. So we have also, as I told you, the horizontal trim. You can use the horizontal trim stabilizer by moving this up and down the pitch trim here manually, or you can use the normal and the alternate trim tab over here, or you have the automatic trim system using the autopilot and flight director system panel. Use the automatic, the auto trim of the aircraft. So the auto trim works if you have the C and the R hydraulics on, C1 and C2 hydraulic system over here. I will show you later. So if you have a malfunction or they not operate, you will have to disconnect from the normal to the data, the C and the R, the stabilizer trim system, so you will have only the manual, not the auto trim from the autopilot and the flight director system. So you will have only the manual trim order like this. So we close the auto trim, disconnect. We have the thrust levers. You can see the takeoff ground. We have we can use the thrust reverse. If I have the speed brakes extended, use the thrust reverses like this. If I move this handle up, it will extend the system, the thrust reverse, which opens the blocker doors and slows down the aircraft on the ground during the landing phase. So you can see the blocker doors here open, and the thrust reverses. Also the speed brakes extend, so you extend again one more time, and also you can use the forward view of the thrust reverse and extend again. So now we will proceed to the next section. We see the thrust levers, the generation of the thrust. We can move one thrust lever up at a time. You can use differential thrust, as you can see. So you'll see the indications here in the upper ACAS of the engine. You can see we have more thrust to the right engine and idle thrust to the left. So we use both the same. We can use the asymmetric thrust to the other side engine, to the left engine. You will see the left engine is moving up. You can use that only during an engine failure. So mainly, so you can see also this is the auto throttle disconnect switch over here. You press this switch in and you disconnect the auto throttle, the one you see over here, which is connected to the autopilot and the flight director system panel. So now we will see the upper and the lower ACAS. So you can see we have the parts that displays. This is the low speed starter and soft, the low pressure compressor and turbine of the turbofan turbojet engine, the N1 stage. You can see the takeoff go around 104.6%, the exhaust gas temperature per engine. We have the left and right engine, the bleeder, the outflow air from the left and right engine, the cabin rate of climb and descent, the total fuel on board. We have also other indications, the N2, which is the high speed starter and sub, the high pressure compressor and turbine of the turbofan turbojet engines, the fuel flow per engine per hour in thousands of pounds or thousands of kilograms, the oil pressure, oil temperature, oil quantity, and the vibration of the N2 stage of the engine in inches. So we can see now we have also here, so we have the left and the right turbofan turbojet engine here and here. We have the landing gear here, external retract, the alternate gear in case we have a failure of the normal mechanism, the lock override, the terrain override, other systems, gear override, ground proximity. We have the external retract limit for the landing gear, the auto brake, maximum takeoff, rejected takeoff, for instance, the flaps limit. You can see the Boeing 777 over here, which is the trademark of our aircraft. And here we have we're gonna see other data of the aircraft. So we're gonna keep talking a little bit more about the engines and how we're gonna use them. So as you can see, we have the General Electric 90 turbofan turbojet engine installed in our aircraft, the Boeing 777-300ER, which is a turbojet aircraft. We have one in the left wing, one in the right wing for symmetrical thrust redundancy. It contains FADEC, the full authority, the electronic control computer that controls and displays and monitors all the data using the upper and the lower ACAS and communication control. The system display the N1, which is the low speed starter and soft, the low pressure compressor and turbine of the turbofan turbojet engine, the exhaust gas temperature per engine, the bleeder from the 5th and the 9th stage of the blades stage of this of the turbofan turbojet engine. We have also the N2, which is the high speed starter and soft, the high pressure compressor and turbine of the turbofan turbojet engine. We have the fuel flow per engine per hour in thousands of kilograms or thousands of pounds, the oil pressure, oil temperature, oil quantity, and the vibration of the N2 stage of the engine in inches. So you can see also the FADEC, the full authority electronic control computer, one installed per engine, dual channel redundancy, one channel fails, the other takes over. Controls and monitors for the data. You see also the engine start, engine shut down, the fuel metering unit, the fuel flow to the engine, low and the high pressure fuel valve, the side of the valve, and also other data like the bleeder and the pressure inside the engine using the bleeder. So we can calculate the pressure inside the engine. If there is an overpressure, the FADEC will calculate it and close. It will open the outflow valves into a higher state to relieve the overpressure from inside the engine. Also, if we have another pressure, it will close them into a lower state, so we will increase the pressure inside the engine. Also, this is useful from as we climb from the sea level. We climbed higher, we have lower air pressure and density, oxygen level is getting lower, and also the temperature is becoming freezing, not below, way below the freezing point. So as we climb higher or as we descend, we have different, we have the half barometric pressure and density and oxygen level, like in an altitude of 20, 30 or 40,000 feet above the sea level. Also, the aircraft flies with an airspeed of about 2 or 3 times faster than that of the sea level. So we have a higher intake of air from the front fan of the engine, which is admitted for compression inside the bleed, inside the compressor, and the starter stages and the turbine, which is mixed with a fuel or mixture. So using the nozzle, so this is generates a different fuel or mixture request every second, and this is being adjusted by the Flught instead of doing manually every second as we climb or as we descend or as we fly. So it's a good thing to have the Flught installed in your engine. So now I'm gonna talk to you about the flight theory of the aircraft. So as I told you, we have the Boeing 777-300ER, and for this flight we have 254,000 kilograms of takeoff weight or 531,000 pounds, which is below the maximum takeoff weight. And we have about 104,000 pounds of fuel on board, or about 46,000 kilograms in the left and the right wing tank. The center tank is empty. It's only 30% of the total fuel it can contain. It's below the maximum. Again, we have about 46,000 kilograms, 46,000 pounds. Yeah, for passenger and cargo, or about 30,000 kilograms. So we are in total 254,000 kilograms of takeoff weight, or about 531,000 pounds, which is below the maximum takeoff weight. Still, for this runway length, we're gonna use the runway 14 in the Zurich International Airport. And the runway conditions, ice, dry or wet, and also the barometric pressure, the density of the air, and the temperature of the air, and the wind direction and magnitude. We're gonna need 15 degrees for flaps and 4 degrees for horizontal train stabilizer for takeoff. We're gonna need to use 100. We need to accelerate the aircraft to 154 nautical miles per hour, or 154 knots, or about 270 kilometers per hour just for takeoff. We need to overcome the stall speed and generate the effective lift. The lift is the force that creates that makes the aircraft fly and overcome the weight that is equal to the mass of the aircraft times the acceleration of the Earth's gravity. So the thrust from the engines overcomes the friction and makes the aircraft moving forward. And also we need to overcome the stall speed during the whole flight. So I'm going to show you also that. You're going to see how the wings generate the aerodynamic lift using the air flow stream, using the Newton's physics per second and third law of kinematics, and also the Bernoulli theory of fluid, and also aeronautical and aerospace engineering principles. So I'm going to show you the outside view now. And then I'm gonna make an engine start demonstration and make a complete flight. So you can see here we have the outside view of the aircraft. So you can see here is you can see the wings, the surface area of the wings hold the weight of the aircraft. In total, you can see we have the mean aerodynamic chord position is about 35% of the Mach, is the position with the maximum aerodynamic lift has been created, and the center of pressure is also the position where the stall begins. The airflow of the air mass above the wings becomes detached, so the aircraft starts a stall. So we have also the mean aerodynamic core position is the position where the center of gravity is calculated for an airliner aircraft. You can see we have the vectors from the left and the right engine, which propels the aircraft forward. You can see the intake from the front fan. You can see we have other things using the center of gravity. We have the vertical axis, we have the longitudinal axis from the nose to the tail, and we have the lateral axis from wingtip to wingtip. So you can see using the center of gravity all the way back to the horizontal or the vertical tail or the left and the right wing, the ailerons and the spoilers. So we have the lever arm or the moment arm from physics, from Newton's physics first, second, third law of kinematics of motion and the Bernoulli theory. So we have the moment arm is times the distance from the center of gravity all the way down to the horizontal tail or the vertical tail over the surface area of the flight control, times the airflow of the air mass per second times the acceleration of the Earth's gravity, depending where we are in the world. So it generates a moment arm to pitch up or pitch down the aircraft, also make left and right turns. So you have control of the aircraft. Also you can see the wings, you can see the bottom surface of the wings is more flat. So using the Bernoulli theory of fluids from physics, the airflow of the air mass as the aircraft accelerates is moving slower below the wing, which generates higher air pressure, which pressurizes the wings of the aircraft up into the air as we accelerate. And also you can see the top surface of the wings is more curved, it has a higher curvature. So the higher curvature makes the airflow of the air mass moving much faster above the wing. So this creates an air suction above the wing, a lower pressure. So we have higher pressure below the wings and lower pressure above the wings, and this creates the aerodynamic lift force, which overcomes the weight of the aircraft over here where is the center of gravity located. So now I'm gonna show you about the flight controls, I believe, and then I'm gonna talk to you about the overhead panels, a couple of things left. So now we'll talk to you about the flight controls of the aircraft. Also, if I use the side stick to control the control column and the control wheel of the aircraft using the elevator and the others as spoilers and also the rudder pedals. So I have complete directional control of the aircraft and stability using the side stick with Logitech Extreme 3D. You can see how they move the side stick, also the flight controls and the yoke of the Boeing 777 and the rudder pedals move accordingly. Also use the pillars for the nose wheel steering in the ground. So this is for the flight controls. So you can see here I'm having this side stick. So you can see I can pitch up and pitch down. You can see the flight control movement over here, pitch up and pitch down, also bang roll left and bang roll right. You can see it's proportional to the side stick deflection, the deflection of the yoke. Also the other side is interconnected, so they both move simultaneously as they should. Also you can see the thrust lever, so over here we can use this over here to move them up and down, forward and aft. We have also the horizontal pitch stream of the horizontal tail over here, pitch up and pitch down. We have also we have the outside view of the aircraft now. How to use the flight controls. So you can see the horizontal tail here. You can pitch up and pitch down, pitch up, pitch down, bang roll left and bang roll right, and also use the yaw vertical stabilizer. Also the horizontal trim stabilizer, so you can see all the flight controls. So now I'm gonna show you the overhead panels, the electrical system, the hydraulic system, the ADIRU, the air balance reference unit, the primary flight control computers, and all the other systems. And then I'm gonna make an engine start demonstration. Then I'm gonna set up the flight management computer and then make a complete flight from takeoff, land, cruise, descent, and approach. So I'm going now inside the cockpit. We have not much time for this video, so So I'm gonna show you another view now of the aircraft over here. So you can see this is for disconnecting the hydraulic fluid. This is the circuit breakers. So you can see the systems again, the autopilot, all the systems depicted. Maybe not much nicer fashion over here. Also the speed brakes up and down. We will use the flaps up 25, 30 and 15 degrees. Over here you will see it depicted in the ACAS over here. You can see also the autopilot better. So we have the APU. We start the APU, the auxiliary power unit, the ADIRU, the aerodynamics reference unit, the thrust asymmetry compensator, the primary flight control computers, the left and the right engine electrical system, the battery primary, the APU as I told you. This is the lighting system, the windshield wipers left and right, the passenger oxygen, the rammer turbine. This is the hydraulic fluid pumps. So we can disconnect hydraulic fluid. You will see what happens. You will see the warnings coming up in a couple of seconds. The fault. So we have many systems fault. Also alternate flaps instead of normal. No autoland. No stabilizer. No hydraulic. So we reconnect the hydraulic system. You can see the system should be working the way it should. Back to the on. The engine driving and the electrically driving. We have the fire extinguishers. We have the electronic engine control, the normal and the alternate mode. The auto start on and off. Normal, we can dump some fuel in flight. We will select the Jenison and arm it. The crossfeed valves, you can see this is the left wing, the right wing and the center tank for fuel. We have the fuel on board, the wing and engine, the ice on and off. You can see the cabin pressurization system, auto or manual. Use the outflow valves, climb and descend and select the landing altitude in the manual mode. Also the bleeder, you can see the left engine, right engine, what happens if we turn off all the bleeder, and also the APU. We need the APU bleeder for starting the engine. So this is the overhead panel in general. So you can see the failure of the bleeder system. We're gonna lose the cabin pressurization and also some hydraulic system. We cannot so bleeder isolation of right. So we reconnect all the bleeder and we're gonna leave also the auto start on. So we're gonna leave the auto start on to start the engines. We're gonna use also this view now the CDU. So you can see the CDU here, the systems. So we have the on display, the engines. You can see the status. You can see the APU is running, the hydraulic and the oxygen level, the checklist, the normal menu, and also the non-normal. We have a failure of a system, the communication, the navigation, the synoptics. You can see the doors are closed and the cabin can be pressurized. You can see the landing gear, the temperature of the brakes and the pressure of the tires. The left and the right engine IDG, the grid generators, backup generator, and also the APU is running the main battery voltage. So this is the electrical outflow chart of the aircraft. For the electric system, the hydraulics, you can see the left and the right engine and the C1 and C2, which is pressurized by the air, where the hydraulic fluid goes in 3000 psi each system. Also the hydraulic fluid quantity, the fuel left wing and the right wing, and the center tank is empty with yellow crosses, the fuel in the left and the right wing, and the total fuel on board. Left engine, right engine, low high pressure fuel valves are on. The crossfeed valves are on. The APU is fed from the left wing using the DC over here, as you can see. So this is the fuel of the aircraft system, and you can see the minimum fuel temperature -37. The air system, left engine, right engine, and the APU is running. So if we increase, this is the bleeder. We need also for starting the engine. You can see the bleeder is increasing on the last system, the flight controls. You can see we use the flight control display to see all the flight controls are working. There is no failures with horizontal trim stabilizer. So this depicts over here, everything is normal. So you can see here also the other side. So this is all in all for this. We go back to the engine, virtual cockpit. So we turn off both engines, left and right, and we go off for an auto start now. So you can see the overhead is reset, and we have about a couple of minutes left. So we can see the shutdown message here, engine shutdown, display ready, there is no fuel flow. So you can see the engines are slowing down now, but there is the engine auto start system is taking over, so we can let the fuel flow on. Left and right engine, you will see fuel flow above 1.5. We have the auto start on. Now you can see the right and the left wing, both engines are running. So only one last step before our flight. We're going to use the flight management computer here, the menu, FMC, position, the model, you saw the model, LCH, set inertial reference, the gross weight, zero fuel weight, the reserve, the cruising altitude 35,300 feet, the cost index 100%, the minimum fuel temperature and the route from Lszh Zurich back to Zurich, copy paste, and the runway 14, departure, select the runway, and arrival, ILS 14, Negri 1 Alpha, transonic, the legs, so you can see the legs here, Negri 1 Alpha, activate and execute. So we have only 15, now we need to use 15 degrees of flaps and the center of gravity to 6%, 133, 140 and 154 degrees gross weight. So we're gonna, just for takeoff, we're ready. So we're gonna tax here. So we advance the thrust levers, disarm the parking brakes and use the tiller for steering. So we have the runway open and we take the runway clearance from the air traffic control already. So we tax here into the runway, use also the tiller and the rudder pedal. So we need to steer over here, and you see we use the tiller for steering the aircraft. So we need to be aligned with the runway. For takeoff, use the parking brakes again. You can use less range here. The LNAV one, the flaps are set. The horizontal trim stabilizer, so we need to use, you can see all the indications are correct. So we use the takeoff thrust like this. And we have one last view before departure and then coming back. Where we are going to go, and here's where we are, and we're gonna use the departure view, disarm the parking brakes and go. So we have about 17 minutes left for this video to end. So we use a full takeoff go on, 80 knots, 100 knots, V1, we rotate, and V2, so we take off. You can see we'd be careful not to hit the tail, so not pitch up too much the aircraft. So we have the positive rate, landing gear is up. You can see we keep climbing, pitch down a little bit, not climb too much. So you can see we keep climbing. So you can see we are 2,400 feet above the ground level, 4,000 feet above the sea level, 5,000 feet now. We keep climbing with 5,000 feet per minute. The pitch altitude is about 15 degrees right now. The airspeed is 235 knots. You can see the heading. Now we are 6,000 feet. And you can see here the airspeed is decreasing now. We have the flaps up. And here we have the stall speed warning somewhere below. So we can see now around. We can make the turn now for following the flight plan as we keep climbing. And we have about 15 minutes left for this flight, for this video to end, for the record. So we keep climbing. We can see the positive pitch rate, and we use manual flight controls for the climb bar. So you can see also, I will show you now a nice view outside. You can see the airport, the Zurich, the Switzerland, the whole of the Switzerland. So we keep climbing. Pitch down a little bit and steer this way. So we can see the aircraft, the outside view over here. Also make the other side visible over here as we climb. Hope you like also the Galaxy. This is our spacecraft for tonight, the Boeing 777-300ER, as we climb through the Switzerland with about 600 kilometers an hour, or about Mach 0.5 or 250 meters per second. So we go with 250 meters per second or 600 kilometers an hour. Right now we're gonna increase that to 980 kilometers an hour or even higher. So make another steering control. You can see again the primary flight display. Yeah, 17,000, and we have about 13 minutes left for this flight. We need to steer through the waypoints. You can see the waypoints here also, the data, the information. So we have the legs. So you can see the German in front of us as we keep climbing. oh, then we have so we need to keep climbing and then make the steer. So we are 20,000 feet above the sea level. So by mistake I deleted a part of the flight plan, but we can still navigate the aircraft. We can have the last waypoint. So we have about 11 more minutes left. We can start retracting the flaps up. $32,000. So we're gonna have the chemtrails in a couple of seconds. You can see the Bayern Munich in front of us, the Germany. So we have the chemtrails, the frozen vapors, and you can see the Germany and the galaxy all around us as we keep climbing and flying. We have to steer back to the airport in a couple of minutes. So hope you like it. This is our spacecraft for tonight, the Boeing 777-300ER. So you can see this magnificent view, and also over here the Germany. So I'm gonna show you a nice view here. I will keep flying. So you can see we cross very close to the Germany over here. So we need to retract the flaps and increase the airspeed like this. Now we fly a little bit higher airspeed, and we keep flying manually. So we are at the flight level here, and we have about 8 minutes left for this flight. We can also connect the autopilot now. So we connect the autopilot. You can see the stall speed, the warning here, and the airspeed we have right now. So we're gonna use a direct 2. So we have to steer like this to the next waypoint. Also use the approach over here to this runway. So we start the descent right now. We left 35,000 feet, still cruising 24,600, and we descend from 35,000. So you can see the frozen vapors, you can see the galaxy over here, and we have the Germany behind us, the France on this side. and we fly with about 900 kilometers an hour, 300 meters per second. We have also the lake, the Switzerland lakes here. So we'll keep descending. We're having the autopilot connected. We use Lszh now. And also the altitude select and the vertical speed. Also extend the speed brakes for this. And you can see we are descending, and we have about 5 minutes left for this flight. So we're getting closer into the runway. Increase also the airspeed. Keep descent. 5 minutes to the runway. For landing. So keep descending, 15,000 feet. The airspeed is less now. Also this is some slow. Now this is gonna slow us down. So you can see the runway here now. We will disarm the autopilot in a couple of seconds. You can see the thrust levers over here. So we need to slow down. So keep descending, 10,000, 11,000 feet now. We disarm the autopilot like this. And we take the manual input now. Also we can use the roll localizer. So we are 9,000 feet and keep descending. So we need to slow down also as we descend. And we have like 4 more minutes left for this video to end. 8,000 feet. We have disarmed the autopilot. We cross over here the river. Also the airspeed needs to become a little bit less. So here we are. And we have like 2 more minutes left. Keep descending. Increase a little bit the thrust. You can see where we are right now as we descend to the runway. So we're gonna have a nicer maybe closer to the touchdown as we descending. We need to increase the rate of descent. 2 more minutes left for this flight. So we can see we have the Lszh localizer over here. All the information. You can see the glide slope. We are 1,500 feet above the ground, 180 knots. The rate of descent of the aircraft and the runway in front of us. So we add a little bit more thrust as we are descending and use full manual flight controls. Here we are. Few more feet. Manual flight controls, manual speed, thrust levers. We're gonna be leveling off. We increase a little bit the rate of descent. Manual ailerons and spoilers, also the rudder pedals. $50, $30, $10. Touchdown. Here we are. As you can see, and we're slowing down to the runway, 80 knots, 60 knots, 40, and we have the runway also. So you can see here we have the nose wheel. You can see everything is normal. There is no breakages of the nose wheel. You can see the metal parts in the tires, no breakages. Also the landing gear behind, no broken wheels on the left or the right side. The aircraft is standing up the way it should be. There is no broken tires and no broken wheels like some other pilots doing. Also the front, the nose wheel is very important. You can see the whole structure of the landing gear. There is no buckling of the metal or broken tires. Everything is normal. Everything you saw. The aircraft again is verified. So the position here. Missouri. You can see also the aircraft is aligned. Control again. So that was Thomas Hatsios, the British American pilot flying the Boeing 777-300ER international flight. Thank you very much for watching. Bye bye. See you next time.